In the next two videos, we'll look at the fifth topic in deep learning, regularization of neural networks. Regularization has been discussed a lot in machine learning, but here we will look at how to apply regularization to neural networks. This video is part 1, and we'll look at how to apply regularization to weights and biases. This video was produced in Korean and translated into English. My voice is AI-generated text-to-speech. Let's take a look at the full table of contents. In the first video, we will look at the overview of regularization and weight and bias regularization. Let's apply regularization by creating a custom loss function and using Keras regularization tool. And let's see how to customize Keras' regularizer. In the second video, we will look at activity regularization. This applies the regularization to the outputs of the hidden layers, not the weights and biases. And let's look at how to sparse the outputs of hidden layers. This is primarily used in sparse autoencoders, which we will look at in more detail later in the autoencoder series. For this purpose, the KL divergence regularization is used. And this can be implemented through activity regularization. Let's think about the accuracy and loss of a model. We have two neural network models, A and B, as follows. There are validation data Y and estimated Y hat for each model. For model A, the accuracy is 100%. And the loss measured by binary cross-entropy is 0.5. For this model, the training loss continues to decrease, but the validation loss never falls below 0.5. For model B, the accuracy is 90%. The second data point is misclassified. The validation loss is 0.22. This is smaller than the loss of model A. Which of the two models is better? Model B performs better. Model A has higher accuracy than Model B, but has higher loss and unstable predictions. Classifying this data point as 1 and classifying this data point as 0 are somewhat unstable. The accuracy may decrease when measuring with new validation data. On the other hand, Model B has slightly lower accuracy than Model A, but has less loss and more stable predictions. The accuracy is expected to remain around 90% even for new validation data. Therefore, Model B performs better overall than Model A. In general, models with lower loss on validation data perform better. Overfitting occurs when you use a neural network that is too wide or too deep for simple data. Regularization helps prevent overfitting. Let's look at the change in loss when overfitting occurs. As training progresses, the training loss continues to decrease, but the validation loss decreases and then increases again. This means that this model can explain the training data very well, but cannot explain the validation data well. Therefore, observing changes in loss can help you determine if overfitting is occurring. Let's look at the change in loss when regularization is applied. Compared to the above model, the overall loss may increase slightly, but both training and validation losses gradually decrease. This model can explain not only the training data, but also the validation data well. It is likely to explain the new validation data well. Next, let's look at how to apply weight and bias regularization to a neural network. We can add the regularization terms for W, the weights of each layer, to the existing loss function as follows. This is the regularized loss function. This example applies L1 regularization to W1 and L2 regularization to W2. And both L1 and L2 are applied to W3. For reference, L3 regularization can also be applied in this way. However, L3 is rarely used because it requires more computation and is not much better than L1 or L2. This prevents W in each layer from becoming too large, preventing overfitting. This loss function is the same as the one we saw in machine learning. As the gradients of this loss function are backpropagated, W's of each layer are updated as follows. The gradient of the loss with respect to W3 is calculated like this. Since W1 and W2 are independent of W3, the partial derivatives of these terms with respect to W3 are 0. The partial derivative of this term with respect to W3 is either -1 or +1. The sine function returns -1, +1, or 0. The partial derivative of this term with respect to W3 is like this. Therefore, we can update W3 with gradient descent as follows. For W2, we only need to use the partial derivative of this term with respect to W2. Bias regularization can also be performed by substituting B for W. Both W and B regularizations can be applied together. This can be easily implemented using Keras dense layer. The kernel regularizer allows you to implement weight regularization according to the formulas on the left. Here you can specify L1, L2, or L1 and L2 regularization. The bias regularizer allows you to implement the bias regularization. The regularization terms applied by the dense class are added to the loss function. We will cover the activity regularizer in the next video. Now, let's create a regularized loss function to implement weight and bias regularization. The regularization can be easily implemented using Keras dense's kernel regularizer and bias regularizer. But to better understand how regularization works, we implement it by creating a regularized loss function. Let's use a dataset for binary classification like this. In order to test with the same data, we saved the data created with the makeBlobs function. Read the saved data. Now let's create a neural network model. The input layer has 2 neurons. The output layer has 1 neuron, and each hidden layer has 32 neurons. R is a regularized constant and is set to 0.001. E is a small value to avoid log of 0. Create an input layer, and then create the first hidden layer. Then we create 4 additional hidden layers. The data is simple, but we intentionally added many hidden layers to the model to demonstrate the effect of regularization. The activation function for all hidden layers is set to ReLU. Finally, we create the output layer. Since it is a binary classification model, a sigmoid activation function is used. And we create a model like this. The results summarizing this model are as follows. This model has 1 input layer, 5 hidden layers, and 1 output layer. The weight W0 of the first hidden layer is a 2x32 matrix. And the bias B0 is a 1x32 matrix. Therefore, the number of parameters in the first hidden layer is 2 times 32 plus 32, which is 96. The weight W1 of the second hidden layer is a 32 by 32 matrix, and the bias B1 is a 1 by 32 matrix. Therefore, the number of parameters in the second hidden layer is 32 times 2 plus 32, which is 1056. There are a total of 453 parameters for training. The trainable variables list for this model contains the following parameters. Next, we define a list of which regularizers are applied to each parameter as follows. This is our list. The first number 1 means apply L1 regularization to W0. The second number, -1, means not to apply regularization to B0. L2 regularization is applied to both W1 and B1. L1 and L2 regularization are applied to W2. And L2 regularization is applied to B2. Next, we will write a custom regularized loss function as follows. The inputs to this class are the regularization constant, the model's trainable variables list, and our list. First, calculate the standard binary cross-entropy loss. Then, for each parameter, we calculate the regularization terms as defined in our list and add them to the loss above. It returns the loss with all regularization terms added. We then compile the model using this loss function. In this way, the regularization can be applied using a custom loss function. Let's check the results. When no regularization is applied, i.e. when R is 0, we can see that the loss of validation data gradually increases. Overfitting occurred because we used a model that was too deep for simple data. Applying regularization to this model reduces the loss of the validation data. The overall loss increases slightly, but what is important is that the validation loss becomes smaller. This is the result when R is set to 0.001. The accuracy of the test data was 0.87. Applying regularization to a neural network can help prevent overfitting like this. Let's run this code. First, let's set the regularization constant R to 0. You can see that overfitting occurs like this. Next, let's set the regularization constant R to 0.001. You can see that no overfitting occurs like this. Next, let's use Keras' regularizer. Read the data used in the previous code. Then we create L1, L2, L12 regularizers as follows. Let's create a neural network model. In the first hidden layer, L1 regularization is applied to both W and B. In the second hidden layer, L2 is applied to both W and B. In the third hidden layer, L12 is applied to both W and B. In the fourth hidden layer, apply L1 to W and L12 to B. In the fifth hidden layer, apply L12 to W and L2 to B. and the regularization is also applied to the output layer. In this way, different types of regularizer can be applied to each layer. The results are as follows. The validation loss is decreasing well, and the accuracy was 0.85. Let's run this code. The results are as follows. Lastly, let's use a custom regularizer. Custom regularizer allows you to implement regularizers that Keras does not support. Custom regularizer can be implemented in a similar way to the custom loss function. In this example, we will implement the L3 regularizer. As mentioned earlier, L3 regularization is rarely used. But if you want to use it for some reason, you can implement it using a custom regularizer like this. If you calculate the absolute value of a parameter to the power of 3, this is the L3 regularization. Then, in the kernel regularizer and bias regularizer arguments for each layer, specify the custom regularizer we just created. Let's check the results. The accuracy of the test data was 0.84. And you can see that the validation loss is also well reduced. Let's run this code. The results are as follows. So far, we have looked at regularization for weights and biases. In the next video, we will look at the activity regularization.